So, as I said before in the previous video, there are three different kinds of snow grains that are formed by metamorphism: facets, rounds, and melt freeze grains. In the previous video, we talked about facets. Now, I want to go ahead and do a deep dive into rounds, talk about their characteristics, the conditions that drive their formation, and why we care. Like facets, rounds have some specific characteristics. They are relatively small grains, and as their name might suggest, they are rounded in shape. So for this video, we're going to represent them with these small circles. Another characteristic of rounds is that, unlike facets, these grains will bond readily with one another. So when I imagine them, I like to visualize them with these lovey-dovey personalities trying to hold hands with one another. And when we're talking about grains of snow that bond well with one another, what we're talking about is cohesive snow. So rounds are cohesive. So we've talked about some characteristics of rounds, but the question remains, do rounds contribute to or undermine stability? And the answer is that it depends on where the rounds are in the snowpack and what they're sharing the snowpack with. So I'm going to start with an example of a scenario where rounds are actually not contributing to stability because they're creating a setup for a slab avalanche. So let's go ahead and imagine the Earth. And on top of the Earth, we've got a layer of facets. So this was early season snow that fell, maybe kind of thinly. And as we've learned before, in order to facet, it experienced a period of cold weather. And then on top of those facets, we've got some rounds. Now, in this case, the facets are going to form the weak layer, and the rounds are actually going to form a slab. So in this case, those rounds are not contributing to stability. Now let's consider a scenario where rounds are contributing to stability. So let's go ahead and get rid of those facets. And let's imagine a snowpack that is comprised entirely of rounds from the bottom to the top. When you look at this snowpack, there's no weak layer and there's no slab. So in this case, the rounds are making up a very stable snowpack. Now I want to take some time to talk about the chemical processes that drive the formation of rounds so that we know where and when we're going to find these grains. So let's go ahead and imagine the Earth sitting constant at a balmy 32 degrees Fahrenheit. Now rounds are really going to preferentially form with two specific conditions. The first is a nice thick snowpack, and the second is a relatively warm ambient air temperature. So because we get to imagine the scenario, let's say it's 29 degrees Fahrenheit rather than 35 degrees and raining. As I've said before, there is water vapor all throughout the snowpack, and if it was properly cold, maybe 10 degrees outside, then that water vapor would be moving upwards in the snowpack, forming facets. But it's not 10 degrees. Instead, in this scenario, we're imagining it's 29 degrees. So water vapor isn't moving upwards in the snowpack. Instead, it's flowing freely all throughout the snowpack. And it's this free-form movement of water vapor that creates the structure of a rounded grain. Now, I'm going to zoom in even further to satisfy the curiosity of any snow nerds who might be watching out there, and talk about the physical process that's actually causing the transformation of new snow into a rounded grain. So here we've got a freshly fallen snowflake, and it contains water in its solid form. Now, the tips of this snowflake are prone to losing water molecules, which will transform into their gaseous phase. And this transformation from solid to gas is called sublimation. Eventually, these gaseous water molecules, or water vapor, will be deposited in the nooks and crannies of the snowflake. So they transform back into a solid. And this transformation from a gas to a solid is called deposition. Now, if this process is allowed to go on for long enough, a snowflake will actually lose its arms and eventually it will take on the shape of a rounded grain. Because of their size and shape alone, rounds are prone to compaction, and therefore they form cohesive layers within the snowpack. But they also undergo chemical processes that drive the formation of bonds between individual grains. So I'm going to go ahead and explain that here. So here we've got two adjacent rounds, which are made up of water in their solid form. And throughout the snowpack, we have water in its vapor or gaseous form. Now, if rounding is actively occurring, then the upper and the lower portion of the snowpack is pretty warm, which means that the water vapor is free to move throughout the snowpack. As water vapor moves between these two adjacent rounds, some of it will inevitably be deposited on the surface of the rounds as solid water. And as more and more water vapor moves between these rounds, eventually what happens is a bridge of solid water is formed between these two individual grains in a process called sintering. And it makes sense why this process would contribute to the cohesive nature of rounds and ultimately contribute to stability if the entire snowpack is built of grains that are linked together. The last chemical process I want to talk about in this video is the process of healing, which occurs when cohesionless snow, like facets, begin to experience rounding, and as a result, they become more cohesive and the snowpack becomes more stable. So let's go ahead and start by visualizing some facets, and they've got awful personalities, which means they aren't bonding well. So in the snowpack, these facets would likely represent a weak layer. And we've got water vapor all throughout the snowpack. Now, when we think about the conditions that created the facets, they arose as a result of cold air temperatures, which caused the water vapor to move upwards in the snowpack. So it was only depositing on the underside of the snow grains, and it was forming these facets. But if the conditions change and the air temperature warms up, then that water vapor is free to move throughout the snowpack. And as a result, it's going to deposit all over those grains, not just preferentially on the underside. And this causes the grains to round, and it also causes the grains to experience sintering and begin to bond with one another. And the end result is that this cohesionless snow becomes cohesive, which is what we call healing. All right, I know that was a lot of chemistry. Thanks for hanging in there, guys. I want to wrap up this video by just going back to the basics and talking about the two conditions that contribute to rounding within the snowpack. The first is a nice thick snowpack, and the second is those relatively warm ambient air temperatures. So kind of anything above mid-20s is going to contribute to rounding. And these two conditions, which lead to rounding, are ultimately increasing the cohesiveness of the snow, which means that rounds create strong layers. So yeah, that's it. Thanks for joining. I'll see you guys in the next video.